Prototype pollution is a problem that can affect JavaScript applications. But before we can talk about prototype pollution, I think we need to spend a little bit of time talking about prototypes and what they are, and then we can talk about prototype pollution. So JavaScript has objects. So we might have a car object, for example, and it might have a color property. So we have a car that is red. Fairly simple. And in some languages you get what's called classical inheritance, where one class can inherit from another and gets to access its properties and that sort of thing. JavaScript doesn't have classical inheritance, but it does have something called prototypal inheritance. And to show you what that is, we might say our car wants to inherit from some kind of vehicle object. So let's make a vehicle. That's another object. And we might say that vehicles by default have 4 wheels. And what we can do is say the car's prototype with this _proto thing is actually equal to vehicle. And what that does for us is it means that not only is car.color available, but car.wheels is available too. So when we try to access car.wheels, JavaScript knows that the car object doesn't have a wheels property, so it uses the prototype instead. And that can happen more than once as well. You can chase the prototype chain all the way up to the top. And we can access it directly as well and say car.proto.fuel, for example, is equal to petrol. And that means that car.fuel, should I say, fuel is available, but also vehicle.fuel is available as well. We affected that prototype object directly. One of the interesting things to note is that all objects in JavaScript by default share a prototype. So if I was to set vehicle.proto. What's a good example? Size equal to large. Or let's go with size is large. Then we'll find that actually the window now has a size property as well called large, because the window object shares a prototype with the vehicle object. So if we can write to this proto property somehow, then we can effectively the global scope. So window is the global scope in JavaScript. So now we have this size variable available. So all well and good. So let's take an example of where this can go wrong and where we get what we call prototype pollution. So this is just a little demo web page that I put together. It's a modern single page application with an about page and a contact page. And we can see we've got one query string parameter here, page equals home. So let's have a look at the HTML source for this web page and see what it looks like. So here we go. We'll just move this out of the way a little bit, or at least we'll try to. Not working so well. Let's move this one instead. Here we go. So a fairly standard looking HTML page. We got two different bits of JavaScript included here. So we have jQuery, and we also have this jQuery plugin query object library being included. And I've included that for a fairly specific reason, but we'll get to that in a second. So we have our h1 tag, which we can see in the page here. We have a div with an ID of content, and then we've got some JavaScript that we'll have a nice detailed look at. So we have an object here called pages, because single page applications are the future for sure. So in here is a set of properties, and each one has some HTML in it. So one for the home page, one for the about page, and one for the contact page that we've just seen. And then what this JavaScript does is it uses this jQuery query is a bit of a mouthful, isn't it? Plugin to get the page query string parameter that we can see here. And then checks if it's empty. If it is, then it redirects us to page equals home. So we can see that happen like that. And then if it's a known page, we set the page content. So we use that as a key for the pages object. And if it's not undefined, we use jQuery to fetch that content div and set its HTML to be whatever the HTML is in this object. So when we click about, we can see we get redirected to page equals about. And this piece of HTML here under the about key is being put into this div. So if we use the elements view, we can see that the HTML is there. So that's all fine. And if you were, evaluating this page to look for, say, DOM-XSS, for example, you might think that it's not vulnerable because, we have no control over the content here. We've got one parameter that is used. It's just a page parameter, and all it's used is as a key of this array. So, how can we get control over some content in the page and maybe get some DOM-XSS working? And the answer here is, as you might have guessed, prototype pollution. So what we want to do is affect the prototype of this pages object and set our own value somehow. And it turns out this particular jQuery plugin query object plugin is vulnerable to prototype pollution. And I know that thanks to this incredibly useful repo from Blackfan, aka Sergey Bobrov. Sergey, I don't know which. I apologize, Sergey or Sergey. Which lists a whole bunch of different JavaScript libraries which are vulnerable to prototype pollution, and some ways that you can try and use that. So we can see here suggested _proto _test equals test. So we can do something like this on the query string here and see if it worked. And the way we can do that is just in the console. We can look at the test variable and we can see it's equal to test. And if we change it to something else, mash the keyboard a little bit, then we can say it's equal to that instead. But also, really importantly, that pages variable, if you remember the one with all of our HTML in it, now has a test property set to this value. And that's because it shares a prototype with the window object. So what we can do is set the page key to be some random value, let's say foo, and then we can use prototype pollution to say that foo is equal to some content, and now our content appears in the page. So we're only really one step off having some kind of exploit here, some DOM-XSS. So let's use image source, empty source, and use the onError event handler to fire off an alert of document.domain. We're in a query string here, so we need to actually escape this equals sign, %3d. And with a bit of luck, we get an alert fired. So DOM-XSS through prototype pollution. Very useful, very handy when it shows up. And like I say, have a look through this great repository for all of the different libraries that can affect. There's a whole host of information here, incredibly useful. So I love learning about new vulnerabilities and new ways to do things, and that was the same for me when I learned about prototype pollution. But I also love automation, or more specifically, as some of you will know, I like writing tools. And if I discover a new class of vulnerability, I want to go off and try and find it everywhere that I can. And a lot of people use things like Nuclei for that, which is, it's a great project, very useful. Or maybe they use some of the tools that I wrote, like Meg, for example. Go and search for reflected cross-site scripting, or maybe SQL injection, or anything like that. But we have a bit of a problem doing that for something like prototype pollution, because this is a purely client-side vulnerability. If I took a test string like we had originally, just test and test, there's nothing about the page source here that gives away that this page is vulnerable to prototype pollution. Short of maybe, fingerprinting known vulnerable JavaScript libraries. But even then, that can be error prone, because we can't necessarily rely on the file name of the JavaScript library when things have all been concatenated and bundled into one single JavaScript file with just a hash as its name. And we also aren't going to spot any libraries that we don't already know about. We're not going to find anything novel that way. So what I would like to suggest is that we use a headless browser to go off and try and find this particular kind of issue. And because I like Go, I'm going to use the Chromedp library. So Chromedp, as the README will tell us, is a faster, simpler way to drive browsers supporting the Chrome DevTools protocol in Go without any kind of external dependencies like Selenium or PhantomJS. And that sounds like exactly the kind of thing that I want. So I'm going to take you through how I would prototype and then build a tool to detect this vulnerability using Chromedp. So let's give it a go. So this is the library that we're going to use. I'm going to switch to a terminal, and I have a directory here already set up called run.js. But there's only one thing in here, which is a list of URLs that are pre-prepared, and we'll come back to those later. So I'm going to make a new Go file called main.go. Apparently I already have a swap file for main.go, so I'm just going to remove that. And I'm using the vim-go plugin, which gives me this template automatically when I start a new Go program. But we'll run through it quickly, what it all means anyway. If you're not super familiar with Go syntax, I'll try and explain as best as I can, but unfortunately we don't really have the time to go through a full Go tutorial. So we're in package main. That means we are writing an executable. So in Go code you can have libraries, so this might be package my super awesome library, for example, that can be included in other Go programs. But if we're writing an executable, we want package main. We've imported the fumped package by default because we have fumpt.println, and we have a main function here, which is what runs when you execute a Go executable, a bit like in C. We have the main function. Now, I, like many other people in this world, am relatively lazy, and if I can get away with not doing very much work, I will do that. And as luck would have it, the maintainers of Chromedp have my back here, so they provide an examples repository containing some more complex examples, and I'm going to use that. So our plan of attack is we want to load a URL like this, have some kind of prototype pollution payload in the query string, and then we're going to look to see if we've managed to set a variable in the global scope. And if that's true, then we should have prototype pollution. It doesn't necessarily tell us if we have, if the page is going to be vulnerable to cross-site scripting, but it does give us a pretty big hint that it's quite likely, or it's at least possible. So let's go with that. So there's an example here in the examples repository called eval, which is what I'm going to use. And if we take a look at it, we can see it does something with a context. We don't know about that yet. We'll have a look. And it does chromedp.run. It navigates to a page, waits until some element is visible, and then it evaluates some JavaScript and puts it into some kind of response variable. So this feels like the kind of thing that we want, or at least pretty close. So let's just copy and paste it, put it into our window, we need to import that package as well. So let's do that. So import, looks like I copied the quotes as well. There we go. Apply some formatting. And in theory, if we run this, we should load google.com, wait for a main, some element with an ID of main to be visible, and then we should evaluate that bit of JavaScript, and then we should print it out, window object keys. So let's see if that works. And it may well not. And if it doesn't, I think the main, most likely reason is going to be that element with an ID of main doesn't exist. So let's just drop that line out. We probably don't want that anyway. Give that a run. And that looks like it did something. So this is a list of all of the variables on the window object on google.com. So it's working, it's launching a headless browser. And I think for me, when making tools, the important thing is to move from one working thing to another working thing in as small steps as possible. If you set out to write a large, complex application all at once, it might work, but you dramatically increase your chances of having a working program if you start with something working and make small modifications until you're finished, or until it stops working, I guess. So let's make some changes to this to try and detect prototype pollution in our example page. So let's take this URL here, and we will load that one instead. So let me forward into here, change that URL to one that we control, and we want to know something about this test variable. And in fact, test is feels like a bit too likely to already exist. So I'm going to change it to a nonsense word, footle, and I'm going to set it to bootle. Don't know why, they're just always the two words that I end up using. So the JavaScript that we want to run is going to be something that tells us whether that footle variable is set on the window object. So we could do something like just get the output of it. So if we just run footle, or maybe window.footle or something, and we try and put the response into just a regular string. We don't want a list of strings anymore. And this is not the window object keys. This is going to be the value of footle, and we run that, and let's see what it does. So we have the value of footle is bootle. So that tells us that this page is vulnerable. But this one exact page in this one exact configuration, this isn't an especially useful bit of code. So let's try and make it a little bit more useful. One of the ways that we could do that would be to have this code accept a list of URLs as input and check all of them somehow. And if we did that, we could, apply this query string that we've come up with here to every single URL that comes in. And we would have a fairly useful but single-purpose tool there that would check for just prototype pollution in the URLs that you give it with this one particular payload, or maybe you could build multiple payloads in. But what I'd really like to do is build something that's a little bit more flexible. So if I come up with anything else that I want to do, running JavaScript on lots of different web pages, I can do that too. So let's start off with just something that takes a list of URLs as input and runs some JavaScript on the page and prints the result. Let's give it a go. So we are going to use a thing from the buff.io package called a scanner to read lines of input. So we'll say sc is a buff.io new scanner over os.stdin. which is going to give us lines of standard input, one after the other. And we'll say for the time that we can scan the input, we will do all of this effectively that we were doing before. And we're going to have some URL. We'll say equal to u, which is going to be sc.text. So that gets us whatever the current line is that's being read by the scanner. And we'll, instead of loading that URL, we'll just load whatever URL we're given. And then we'll evaluate window.footle for now, why not? And this log fatal in the middle of the loop I'm not especially keen on, so let's change this instead to a log.printf, where we print the string value of the error and say there has been an error of some kind. We don't need a new line because we're using a log package. And then we will continue in this loop instead. Now, if I try and run this program, it's going to tell me that I've got some some packages that I haven't included, so I'll just do that real quick. And if I run that, it's just going to sit there. And the reason it's sitting there is it's waiting for us to put in some kind of URL. And we can see we got an error on example.com, encountered an undefined value. And that's because it's looking for window.footle, right? And that doesn't exist because why would it? So what I'm going to do is say, actually, I'll use bang to execute a shell command. I'll run go build in the current directory. And I want to cat my URLs file into this run.js program that we've been writing. So we were in a directory called run.js, and therefore Go decided that's what the binary should be called. So let's run that and see what happens. So we got encountered undefined values. On one of them we got the value of footle is bootle. We don't know what for, so let's fix that. And instead of saying the value of footle, let's just put in the URL that we were calling instead and see what that looks like. So we're running, we expect the output to be, oh, I read the wrong thing. I want to run my go build command again. So we'll run that, we count undefined values for some of them, and on others, on this one, we got this value bootle. So that works okay. It's a little bit strange though to always just run this window.footle. I wouldn't expect a user of this tool to be able to, guess or remember that that's for some reason what you had to do. So let's change this instead to be some value called user.js, and we're going to accept that as a flag. So we'll use the go flag package, and we will make a string variable, and let's see if I can remember the order of the parameters here. So we're going to have var user.js, which is a string, and then a string variable of user.js with a default of empty. I'm trying to get this right. Oh no, first comes the name, so we'll make that J, a default of empty, and then the help output for it is going to be the JS to run on each page. Okay, so now if we run this, it will tell us we haven't got the flag package. Now we do, and it's going to go off and run some empty JavaScript on every page. But if we change our command to say, let's include window.footle again, hopefully, with a bit of luck, we'll see one of them in there works just fine, which is great. That's exactly what we wanted. Cool. So, we have a kind of reasonably working tool, I think. I think maybe the output could use a little bit of fixing up. So I think the log of the error, for example, could probably stand to tell us what URL we were using. So let's fix that. And let's have a quick play with the tool and make sure it does exactly what we want. So our URLs file kind of already has these payloads in here, and we could have them in there manually, or we could add them in with some kind of bash magic. So if we pretend, for example, that we only had the first part of the URL without the path or anything like that, we could add it in that way. So we could take now I have to try and remember how to use my own tool. Let's have a look at the help output for unfurl. So unfurl is a tool I wrote for pulling up our URLs. So we might have the scheme, which is %s, and then we want the domain, which is %d, and then we probably want the path as well, which is p. So there we go, we've got those all stripped off, and then we could do something like awk print $1, which is just the URL by itself, and then we could append the query string that way. So we could say proto, let's use something other than foo. Let's just use foo is equal to bar, and that gives us a whole bunch of URLs that have this query string appended to them, and then we can run that through our run.js program, give it some JavaScript, and say, well, we want to know the value of window.foo, and see what happens there. So we have something I had set up previously here, which is prototype pollution example running elsewhere, and that's come up and said bar, which is kind of useful output, I suppose, but we could probably do something a little bit better and say, let's use a ternary operator to say if window.foo exists, say vulnerable, otherwise say not vulnerable instead, and we'll see what that looks like. So now, instead of getting that error on all the ones that don't have the prototype pollution issue, we just say not vulnerable instead. So that works reasonably well. I think we've done a fairly good job there, but there's still probably some improvements that we can make to this thing. One thing that I think is pretty common across a lot of bug bounty hunters especially is that they like to look at a lot of different targets. So, I have a list of several URLs. How many was it? 7 URLs. How often do you have 7 URLs you want to look at? You could do that manually. There's not really much point in writing a tool to check 7 URLs. So let's add some concurrency to this instead as well. And hopefully maybe we can check things a little bit faster by introducing some parallelism. So the way I tend to approach adding parallelism in Go programs is to have some kind of pool of workers, and then use a thing that Go has called channels to communicate the list of inputs to them. So let's do that and see what that looks like. So we want to set up maybe, let's say 5 workers for a concurrency level of 5. So we'll say for I is equal to 0, I is less than 5, I plus plus. Go only really has for loops, which is actually one of the nice things about it, as far as I'm concerned. We're going to run a Go routine, which looks like this. And a Go routine is a function which runs asynchronously, effectively. And what it's going to run is all of this stuff. But it needs to get that from some kind of input. So let's make a channel. and we'll make that channel called URLs. So I'll make a channel of strings, and then each go routine is going to read from that channel. So we'll say for u is equal to the range of URLs. That's how you read on a channel in Go. We are going to take URLs off the URLs channel for as long as we can, and we are going to run our headless Chrome code against them. We've got a couple of things to clean up here though. So one of which is this defer cancel. This was kind of fine using small volumes of URLs, but if we're going to be using lots, these are all going to stack up until we've finished at the very end. So we are not going to call cancel there. Instead, we are going to run it, let's say here, after we've finished doing all of the things we need to do. That should be fine. Okay. But if we try and use this, well, so far we're not actually adding any information to it, so it'll just pretty much tell us, u is not declared, but is declared and not used, which is which one? Oh, it's this one here. So what we actually need to do here is send this uText on our URLs channel so that it gets sent to all of those workers that we've just span up. So let's give that a go instead and see how that works. Kind of worked. So we've got, encountered an undefined value. That's fine. That's just because we're, that's exactly what we're doing, and on these pages there isn't one. But more worryingly, we only saw 2 of these before it stopped working. So let's try again, and we only got 2 of them again. So what gives? And the answer is, we're creating a pool of workers reading from this channel of data, and then we are writing all of our input onto that channel so that they receive it. That's fine. But as soon as we've done writing it, we hit the end of our main function and we stop. Go doesn't automatically wait for your work to be finished, because it's perfectly legitimate that you wouldn't want that to be the case. But we can use a thing called a wait group to coordinate our worker pool and wait until they've all finished doing their thing before we stop. So let's give that a go. So somewhere around here, probably, maybe just before we make our channel for URLs, we're going to make a variable called wg, and that's going to be something from the sync.waitGroup package. And every time we launch a Go routine, we're going to call wg.add1 to say we're adding one thing to this wait group. So what a wait group does is you add tasks to it, or effectively just sort of placeholders to say, I am doing something. And then when you're done, so when the channel's closed, we can call waitGroup.done in each Go routine. So what that does is, when we create the Go routines, we add one to the wait group. We create the Go routine, which will read input from the URLs channel until the channel is closed. That's the behavior of range. And then when that's closed, we'll call waitGroup.done. And that effectively subtracts one from the wait group. And then down here, right at the end of our program, we can call wg.wait. And that's going to sit there and block until, hopefully at least, all of our Go routines are finished. So let's give that a go and see how it does. So looks like things worked. So we have our bootle value for this one. The rest of them, we encountered an undefined error. We can quit out of this and run our previous command and give it a go. And hopefully you can see things happen a little bit faster now, which is pretty good. I think that's something that we would want from a more concurrent program. So hopefully this gives you a bit of an idea of firstly what prototype pollution is, but also how I might approach writing a small tool in Go, or the principles apply to nearly any language. I think the important parts for me are have a problem to solve, but as you are working, move from a small working program in small steps to your eventual working and potentially complex program instead. And also, where there's very little overhead to doing so, it would be a really good idea to make a tool more generally useful. So to give you an idea of what I mean, if I take my list of URLs, I can run through this run.js program, and let's say I wanted to know about what's a good example? Any cookies that were set. So document.cookie. So I can run this, and I can see that on tomnomnom.com, man, not being able to say your own nicknames, pretty bad. There's these UTM-A and UTM-C cookies being set, and on the other ones there isn't really anything. Or maybe we might want to look for links that are in the page. So we might say document.getElements by tag name, and have the A tag, and we will use the spread operator to turn these into an array, so we can use a map operator on them, take each node and get the href value of it, and then join them together with a space, for example. I've just seen some single quotes in there that are probably going to mess with us. I'll change them to double quotes, and there you go. The output's not super pretty, but you can see it's working. We're getting the href values from each page. So httpbin.org seems to have the most of them in there, including a mail to me at Kenneth. So, we set out to make a tool for prototype pollution, but actually we ended up writing something that was more generally applicable. So I hope that was useful for you, and I hope you're tempted to go off and write your own tools. I think with a little bit of practice you can get quite fast at it. I know there's a real temptation to think, I'm going to spend more time automating things than I am just doing some hacking or just doing the task in the first place. But within a matter of 20 minutes or so, it really is genuinely possible to write actually useful tools. Thanks.